Well, before we get into geometric vector proofs, this is a bit of a preliminary look at some of things that we will be using and also some of the skills you need. So firstly, some definitions. You need to be across collinear points, and collinear points are where there's three or more points all on a single line, like those 3 points. Concurrent lines, or pass through or meet at the same point. You need to be across vector addition, geometric vector addition and subtraction from your previous studies of vectors. You need to understand the nature of parallel vectors as well. So with parallel vectors, Ka is in the same direction as A. It's a scalar multiplication, so that means we have K as a positive real number. If it's negative A, it's parallel, but it's in the opposite direction. Okay, so basically we've seen that before. Two non-zero vectors are parallel if and only if B equals Ka, where K can't equal 0. And vectors A and B are parallel when at least one point in common lies on the same straight line. So those things are important. As is scalar product. We'll be applying that at times. Now remember, when two vectors are perpendicular, the dot product or the scalar product is 0. If we go A dot A, it comes out as the magnitude of vector A all squared. Remember, a scalar product yields a scalar. Linear combinations of non-parallel vectors. So if we have two vectors that aren't parallel, if m times A plus n times B equals P times A plus Q times B, then m equals P and n equals Q, which was looked at in a previous topic. Lastly, the scope of our proofs, what we will be including are the following. We'll be basing it on quadrilaterals, regular ones, and mainly parallelograms. Just make sure you realize that a parallelogram is basically the shape which can yield three other common shapes. The rhombus, which is a special case of a parallelogram. The rhombus is a parallelogram with all four sides equal length, which is a special case of the parallelogram. Alright, there's our parallelogram and there's our rhombus. There's two other special cases of the parallelogram. When the angles are variable, when all four angles are equal to 90 degrees, we have a special case of the parallelogram called a rectangle. Amazing. Yes, there's this thing called a rectangle. And it is a special case of a parallelogram. The sides are the same as above. However, the angles are a special case and they can be 90 degrees. Thus, if we put those two variations already together, we've got the square. Alright? Yes, the square. It's amazing. The square. Hours of fun. The square is basically a mixture of the other two special cases. We have 90 degree angles and equal sides. We'll be dealing with things such as diagonals and side lengths or midpoints of sides of quadrilaterals, and we'll be using properties of parallel and perpendicular lines, which we talked about above there. So for example, it may use dot product, or it may use scalar, the product of a vector by a scalar. See you in the next video.